In this video, I want to give you a little more practice and understanding of op-amp circuit analysis. So let's start with this op-amp circuit. This is actually rather simple in the grand scheme of things. Let's say we want to find VO, and let's suppose VA is known as well as RF and RA, and VCC also. These are just givens. Let's start with op-amp assumptions. By definition, this is 0 volts, and 0 amps comes in here. Also 0 amps. And because of the virtual short, why this is also 0 volts. Now it is straightforward to write a KCL equation so we can solve for VO. So the currents leaving this node here are as follows. This allows us to solve for VO as a function of VA. And now it's easy to identify the gain. Output over input voltage. And so that's the ratio. Immediately we can see that the gain is negative, so this is an inverting amplifier. The other thing is that we can choose RF and RA. So we can choose between amplification, attenuation, or neither based on our choice of RF and RA. A couple important principles there. So we know about the gain. Let's talk a moment about the linear range of this amplifier. So given that the output is VO and the input is VA, well, we could identify that there is a linear relationship between these. The slope is negative RF over RA. So I've drawn it as negative and passing through 0. Well, this amplifier, since its power supply is VCC and minus VCC, it cannot produce more than plus or minus VCC volts. So we'll go ahead and write this here. So the output of this amplifier is going to look like this. We can vary VA over some range, and it's going to result in some VO, but as soon as that VO reaches plus or minus VCC, we could dial up VA or dial it down, and you can't get any more than plus or minus VCC. So we'll identify this as the linear range. And so we can solve for what that is. Basically, we have VO, right? It can't produce any more or any less than positive VCC or negative VCC. And then, using this relationship, we'll write like this. And now we're going to multiply both sides by negative RF over RA. And then we have to reverse the signs, so I'm going to do all of that in one step. Okay, so I've divided by RF over RA times negative 1, of course. Reverse the signs. So that's our final expression for the linear range of this op-amp, which we could also write like this. Completely equivalent. So we can write in our plot the following. And of course you could plug in the numbers if you had numbers for RA and RF, and then you could maybe have a little bit more specificity on this result. So in this video we've shown you the gain, we showed you how to come up with the gain, and then we showed you how to come up with the linear range. We'll do a slightly more complex example. So here's the more complex example. It turns out that here's our VO, so we'll need to reassign this as Vx. And so we can apply the same op-amp assumptions, and we get the same KCL as before, except now we're using Vx. And this leads us, of course, as before, to Vx being this. But Vx here isn't the output. The output is here, and what you can see here is that Rb and Rc are in series, right? They're connected by one node, no other current carrying connections. So we can use voltage division to get VO. And now we can combine these two expressions. So we can write VO as a function of VA. So this behaves exactly like the previous example. And this, we know, has to be less than 1. So for completeness, we'll identify the gain. And we can talk about the linear range. Here, our constraint is that it's Vx that can't be more than or less than VCC and negative VCC, respectively. That leads to the same result as before, where you can put in here so we get the same linear range for the input, but let's sketch this output versus input. Here the output is VO, the input is VA. Just like before, I'm going to plot a line that's of slope negative RF over RA. This is Vx over VA. But notice that VO over VA is this, but times something that's less than 1. So I'll sketch that as something with a lesser slope. And we'll say that that slope is A. And we already know the expression for A. We already know that VA gets us a linear response. So the only thing now is figuring out what this plateau is. Where does it saturate? And so basically you can take this and then you multiply it by the remaining part, right? Because like this is our VA max. And so we plug that into our expression for VO. So we plug VA max into our expression for VO, and we have an RA over RF that cancels with a negative RF over RA to a negative 1, and then we're left with a VCC, and then we have this factor there. So basically, we can then say that this has to be as follows. Okay, so we started off with a simple inverting amplifier or attenuator, depending on how you choose RA and RF. We showed you how to find its linear range, right? The output can't be more than VCC or less than minus VCC. Then we took the same circuit and we added a couple of resistors. So now you have, instead of taking the output at the op-amp output, you take that op-amp output and you do a voltage division. It's going to reduce that, scale it down a little bit. And so what it does, really, is it scales the plateau by that much, by that voltage division. But we still have the same maximum and minimum values of the input. So a couple cases of this inverting circuit, and then one we just add a little complexity by doing a voltage division at the output.